Okay, let's start. I just before starting the lecture, I wanted to talk a little bit about homework 2 and reflect on it a little bit. And the reason for that is that one of you guys showed up for my office hours, and I realized that maybe people did not fully understand how to use those tools. And I just wanted to make sure that we all are on board, because it's just one thing is to just sit in this class, listen to the lectures, maybe even pass the exams. But the real goal is to kind of learn how to use those tools, learn how to debug stuff, like to the level of the individual assembly instructions, stuff like that. And that's the whole point of the class. So if we're not doing that, it just doesn't make sense. So what I'm doing here is by no means I'm an expert, and it's my first time using Visual Studio Code, or virtually the first time. And I set it up looking at the instructions for your homework number 1 and homework number 2, right? So just blindly follow the instructions. And instructions were created by the TAs because I usually use SSH. So I actually don't mind Visual Studio Code. It's pretty cool, to be honest. But usually the way I do it is this way. So let me just move this somewhere. Oops. So I'm a little old-fashioned, so I just go into the I detach my screen, so I just SSH into the CAD machine, and I use screen again, a little old-fashioned versus Tmax, but that's what I like. That's how I build those homeworks, right? So I just I can do. What I did, I just again, if you're curious, I just simply downloaded the files from online. It's homework 2, just verbatim. Download it from the web as it was given on the assignment homepage. Where is it? Let's go here, cs5460. So just downloaded these 3 files from this homework, right? So the ones which are given here, elf, main.c, and makefile, right? And but I strongly support the use of Visual Studio Code. It's all cool, right? So what I did here, I just like I said, followed the instructions. What is that? Connected to this machine. So and this is what I'm running. So where is it here? I went to my cs5460 folder, downloaded all these files, right? Created this JSON. And what I wanted to demonstrate here is, not surprisingly, just the very same thing as what's there in a homework. The first question, explain the crash, right? And I just simply say, okay, start debugging. It runs. Okay, I already had a breakpoint here. Let's run again. Cancel, let's stop it. Let's run again. Okay, so what has just happened? So who can tell me? We did a run on CAD. I assume you did the same run in your homework if you were using CAD. It returned, right? So it didn't crash as opposed to the instructions in the homework. Do we agree on this? Is that what you all guys concluded? That it didn't crash? Okay, my next question then, why it didn't crash? What's the explanation? And to be honest, my main thing is this. Okay, maybe I cannot believe my eyes to begin with. Maybe it just somehow didn't even call the quadruple function, right? So because it ran, it just said, okay, loaded relocation table, yada yada, return 0. So this printf executes. But maybe quadruple is 0 or something, like null, right? Or not 0, whatever. I don't know. Maybe it just didn't run. So let's add the breakpoint, right? Let's run it again. Okay, cool. We are here. So what do we do next? I say, look, sure. The instruction tell you open this disassembly view. Where is the body? Do we even have it here? That's a little weird. So look, it used to be here, but now disassembly view disappeared. Am I right? I don't know why it disappears, but it's not there, right? But I've seen it before, and you've seen it before, right? I mean, if someone knows the answer what to do, maybe restart Visual Studio. We'll try in a second. But there is no disassemble view, right? So what do we do next? Like somehow it disappeared. Like there is a bug in Visual Studio. I don't know why. I don't know where it went. Maybe it's hiding somewhere. Maybe it's somewhere here. Where is it, buddy? No, nowhere around somehow. I mean, so what's the suggestion? What do you guys suggest to do? In what? Can I write here? Right click here. Breakpoints, main. What do you suggest to do? Right click. I mean, 2 fingers, 3 fingers, doesn't right click. Oh, now it's here. Maybe it was here. I don't know. Okay, cool. So we are here. So what does it mean? Where are we running now? What do we do next? So Visual Studio says that we are executing this line. In assembly, it's this line. Anyone? Can we interpret this code? What is going on? Where's the invocation of quadruple?
The yellow line at least is checking if quadruple, so it's comparing it to 0.
Correct.
Yeah.
So we say, okay, it's a function pointer. We have a couple of options here. We have this thing which says step over, meaning do not go into the function, or this one which says step into. So let's step into, compare the instruction of the function pointer. We say, look, wow, if it's equal, then fine. So what do we do now? What is this instruction? Allocating space on a stack for what? No, to go, but more specifically. To do what? Correct. It allocates the space on the stack to, in the next instruction, it actually pushes. Yeah, it looks like it's for alignment, which is a little weird, to be honest. Probably alignment, because the pushes the argument, right? Okay, we push 4 into quadruple. Is that what we're doing here? Yeah, correct. Yeah, so we're happy with this. What is this? What is this line? Uh-huh. I think so. And that's, I don't exactly know the reason, but one explanation which I found online, and we can spend a second and Google online, is that, I mean, it's a convention at the level of the compiler, right? But I think my understanding that the origin of this convention is that some MMX instructions can only operate on aligned arguments. And that's why they maintain stack alignment. So it's we subtracted 12 and then pushed another 4, so which probably gives us 16, right? That's my understanding. But back to, like, good, answered the question. Okay, so what is this line which we're executing? What is this line doing? Anyone?
The call to quadruple, we stored it in a pointer like an array, so it's just moving that into EAX.
Correct. So this is the implementation of a function pointer, right? Because right now, like what we're doing here, we say quadruple, which is defined as a function pointer, is just literally a pointer. Where is this guy? This one, right? So it's a definition of a function pointer in C, but really just like any other pointer, it can be a pointer to an array, pointer to something else, right? In our case, it's a pointer to a function. And this is the syntax how C wants you to declare this pointer. It says, okay, it's a pointer to a function which takes an integer as an argument and returns an integer, right? Agree? And so this is how the compiler implements this pointer. They say, look, the pointer itself is stored in this EBP minus XC. It's relative to EBP, so it's a local variable. And so we will just load it into the EAX register, right? And then immediately after that, we're going to call it, right? And okay, so this is the actual call to quadruple. And so if we say, look, we step into it, well, we step somewhere. This guy, I don't expect this guy to understand where we are because it doesn't, like there are no symbols for the L. We just loaded like something from disk into our memory and we stepped into that memory. Visual Studio Code doesn't understand where we stepped. It's possible to like probably do some plumbing to explain it, but that looks nice. And if you do the obj dump of this elf, you exactly, like you will understand that it's exactly there. So if we, for example, either like I'll switch to the term which I like so much, and I do something like we have the elf file compiled, obj dump help, and I want to disassemble. Sorry. My pipe into grab disassemble. It says disassemble all minus D. Thank you for everyone. Obj dump. So that's not fun. What did I did wrong? Something wrong. I think it was my. Yeah, agree. Lowercase d. Oh, well, yeah. So it says, okay, quadruple really looks like this, right? Like, so it maintains the stack frame. So it pushes EBP, moves something, then does the multiplication. Agree? And so that's exactly what's going on here on this screen. So it pushes EBP, maintains the stack frame, loads the global variable, and in theory, like this is how the assignment was created. It should crash at this line. So it should have crashed here in a previous line. Why is that? Anyone knows? Like, do you agree that it's supposed to crash in the back? Correct. So it really just says, okay, here's the global address. I'm going to use it. And I load something from there into the register. And in fact, if we want to see what it loaded, I don't know if Visual Studio will show you here. Like, do we know how to take a look at the registers here in Visual Studio or not? Does anyone know? Hold on. So I switched to, like, just give me a second and maybe I will help it. So let's say, like, there is this debug console, like, because what's going on here is that Visual Studio just connected to the GDB. It uses GDB as a backend. And this thing actually says, okay, you can issue a GDB commands explicitly with this exact argument. So if I say something like exec info registers here, it will like faithfully send this command to GDB. GDB has like a connection interface, and it will like dump me the registers, right? So I can actually execute any GDB command from this interface as well. And this is what I wanted to show as well. And so what it loaded here, let's take a look. So in the EAX, it loaded 0. Why is it 0? Can anyone explain? That's the beauty of C. C doesn't, I don't think C has a default. I can be wrong. Not a big expert on C standard. There's a hand in the back. Dave. Uh-huh. It's value 0, correct. So it just loaded. It basically, okay, so how do we even like dump those values from like, what if we want to confirm that something what is contained at this address is actually 0? Wow, to be honest, I mean, I use GDB every so often, so I keep forgetting how to use it. And I say, okay, look, sure, like I'll just go here, GDB, dump memory at address. So it's almost like ChatGPT, but okay, fine. Still the old search. And like it says, you can do something like print X and this address, right? Like P stands for print. So let's try it. So PX, are there any other alternatives? Not so much. So, okay, sure, PX. How does it? So I have to exactly send this command to GDB. So it's PX, is it, if I remember correctly, copying it PX, okay, and the address, which was this, okay, OX 8048 1D. Let's try it like this. That's old. So what is that we're doing? So like this maybe? Yeah, so it wants an address. And what if I want to dump maybe 16 values? Oh, not like this. Maybe 16 somewhere here. No, doesn't work this way. How does it work? Not on this dump value. Dump 16 bytes at address. The point which I'm trying to illustrate that you actually can, okay, so this is the syntax. Okay, it wants this X. Sure. Not sure what the P stands for. X. What? 16 byte as hex, like this. No. X. What did I do wrong? Okay, got it. Thank you. Yeah, you see, you use it more than I do. But okay, so here we go. So this is, I just dumped 16 bytes. Maybe if I remove B, it will dump me. Wanted to say as integer, but forgot how to do it. But anyway, so okay, so believable. That's essentially, we inspected memory and we can dump a little more if we want. If we don't want to look at bytes, there is a syntax to say something like, I forgot what, I or something. Dump as instructions. Oh, wow, it actually can disassemble it as instructions or something. But the point is that you can actually access the memory, right? So it's believable. It loaded this memory from address 0, or from this address, and it really contains zeros, right? That's why it's a 0, and it didn't cross, right? So it faithfully does, by the way, like along the same lines, although I was clicking this blue error. How do we, I don't have to click it. I can actually control the GDB from this exact interface, right? So how can I step one instruction in GDB? Do you remember? SI, exactly. So, and like in this next homework, we give instructions for how to use GDB, just to make sure that you guys kind of warm up to this idea that GDB is a decent tool. And since it's used as a backend, sometimes it's needed. So in this specific example, when a student came to me, we were talking and this like exact view disappeared somehow. We didn't know. So we did everything from GDB, right? In fact, what we did something like here it shows you what are you executing, but unfortunately it doesn't know which instruction you're executing because like in this view somehow GDB doesn't report what's going on. But you can do something like disassembly and say, well, can you disassemble near the like again, I didn't know how to do it, but okay, maybe like this, EIP. No, it just doesn't want me to do. Okay, sure. Back to this, back to the helping thing. GDB disassembly current EIP. So something along those lines. What does it say? Okay, cool. Display. You can do a program counter. But why display? I want disassemble. Okay, sure. But if we do this, well, it shows the same instruction, right? But there is a way to, what if we do like 16 maybe? What does it show you here? Yeah, so then it can show you like, for example, like some number of instructions. I said 16 in that window. So if you're confused about what's going on, you can also like directly communicate with GDB. And okay, I keep stepping those instructions. I say, look, I just want to see that it executes. So it loads again the value from this memory. So it like actually follows in that window. If you don't want to do it, you can like you can keep disassembling the instructions, right? And it's like it shows you here, right? So you can display instead of doing this, we can do like, I don't know, 4 instructions here just to make sure that we are there. We see it on the screen. So it does multiplication. Results of this if you do exec info regs, you will see that whatever the result which you got, like whatever you got in the EAX is 0, so it multiplied a couple of zeros, got 0 back. And if you keep executing this thing or like switch to this view, you essentially popping the EBP, returning, and like going back to main. So now we're currently here. We got the quadruple. We say we don't want to step into the printf function, but that's essentially like printf executes. We can see it on the output here. Hopefully, somehow didn't show, but where's my output terminal? Probably, yeah. So it's here, right? And okay, cool. So it keeps running and finishes correctly, right? So it didn't crash. That's the answer. Do we agree on this?
So I did notice that occasionally it will have a segmentation.
Yeah.
I don't think it's.
Yeah. So did anyone else observe the same? People did, right? So, okay, so what's the explanation? Why it crosses or doesn't crash? What's going on here?
Well, it's hard to know.
Correct. So what you're saying is that really the operating system itself, Linux, which we're running on KID, right, construct the address space. There is even a possibility that it uses a technique which is called address space layout randomization, which means that it constructs a slightly different address space every time, just to confuse the attacker. I don't know for sure if KID does it. Most likely they do. But essentially, every time you get a different address space, and what happens here is that in reality, you just randomly access an address in a program. And it so happened that the address was mapped and was readable, right? It can be, we can take a look at what really, there is a way to see the layout of a process. So on Linux, if we really want. So we can take a look. But in practice, it just so happens that something is there and you didn't crash. And it can happen in production. So you can like really build a program and your variable, just a pointer, points somewhere randomly. And maybe it's like a piece of readable data or readable code if it's mapped as readable. And you just read the values. And what you have to observe is that just the value, this return address, the return value is 0, is incorrect. So really should, if you're passing 4, you should get something different, right? In a correct execution. So it may go weirdly south, right? And you have to be aware of this, that because as I was saying, the goal here is to understand that CPU just blindly executes instructions. If you messed up your address space, doing something funky, like we loaded an ELF file, didn't relocate it, then you can access any random locations in memory. And it can happen that you finish execution as well. So that's the observation, but I wanted to make sure that we all understand how those tools work. I also wanted to understand, to make sure that we understand that you can invoke, you can use Visual Studio's Visual Code, Microsoft Visual Studio Code to attach to GDB, get all those answers. You can also use it from command line GDB. Okay, let's start GDB, start a program with arguments because we want to pass an arg arg. And we say, look, we don't remember how to do it. So it's like this. GDB args, executable names. Okay, sure. We can say this args. Executable is main. This is, if I do L, what is L? Supposedly should be GDB has support for this graphical user interface. We can scroll there. We can say, look, let's put a breakpoint at quadruple, for example. Keep scrolling a little. So it's a breakpoint on main.c, line 317. Then I say run. I got here, right? It's exactly what I was doing in Visual Studio, but just wanted to make sure. Layout ASM, it shows me the ASM, just exactly what we were seeing before. I can do something even like layout split to make sure that I see both. And I will do step instruction. It just executes this jump. Remember, comparing to the function pointer, not 0. Align stack, pushes the argument, calls into EAX. Now it lost the source file because it doesn't have debug symbols. It says, okay, I really started executing the address, which was not compiled into the program, but it faithfully shows you here the assembly of this program. So we can do the same thing like info regs. And I keep saying that it should be. So it's exactly the same thing. So registers are here, step instruction, go. If we can, it's the point which I'm trying to make, that GDB is quite, friendly and convenient, really. And sometimes, I would assume that everything what you want to do in GDB, you can do in Visual Studio C, but just make sure that you at least know the GDB commands to make sure that you can finish your task. And here it returns, it says, okay, guys, I actually did the quadruple function, I didn't crash, I got to next. And at this point, I probably stopped executing, right? So, and this attempt, I advocate for using both essentially, or at least understanding that both tools are usable. Okay, so that's what I wanted to show. Any questions about it? Okay, cool. So apparently, everyone is a reasonable expert on GDB and everything. So we'll continue using it, we'll continue using both essentially. But we will in this next homework, we will probably ask you to use a little bit of GDB. And if you're completely stuck on it, then you can switch to Visual Studio Code again. Okay, so then let's get back to the lecture. So do you guys remember what we were trying to do? We were trying to essentially make sure that what we're trying to create, we initialized kernel memory allocator, which keeps track of available physical memory in the system, right? And actually, since we couldn't initialize the allocator to cover all the available physical memory because we actually have to map it, and we currently only map the memory up until the 4th physical megabyte, we only initialized the short list, and later on we will initialize the rest of it. But the idea is that, okay, we have enough memory to start constructing the page tables, and essentially our goal was to construct the real 4 kilobyte page table, and essentially like switch to that new page table. And the thing which we were doing is that like the first two functions, we looked at the very first function in x86. It was this one, initialized as the memory allocator. Now this one will create a first kernel page table. And at a high level, what we try to do is we say, look, we will treat the memory as a collection of regions. And the reasons for that is that they have slightly different mappings. So we have a total of 4 regions, like this 1, this 2, this 3, and this one is 4. And this one is writable, this one is read-only, this one is writable, and this one is writable as well. Mostly it's done to make sure that, okay, there is some write protection, like in this example, which we just saw in GDB. If you're trying to write into the kernel text, somewhere over here, you will immediately get a page fault. It kind of protects the integrity of the system. So guards against certain class of bugs, but also like to make sure that we have some generality in the kernel, and we say, look, we can maintain multiple regions, and then we'll map them separately. But at a high level, what will happen is that in order to construct a page table, we'll create a couple of helping functions which work like this. You start with a specific physical address, a page which sits here. Start with a virtual address where you want to map it. You take this address, virtual address, you split it into 10 bits of index into the page table directory, 10 bits of index into the second level page table. And you assume that this page table directory is already allocated. So you just say, look, this 10 bits will point me to an entry in the page table directory. So imagine this entry is this one, yellow. Then here you say, look, depending on whether this entry is present, the bit is 1 or not, you say it may be that the second level is allocated or not. As we will go forward, we say, like, if it's not allocated, we say allocated. This goes into memory allocator to that linked list which we created, allocates the second level page table. We connect them by like essentially writing the physical address of this second level page table into the page table directory. And then we use the next 10 bits saying, okay, look, those 10 will pick an entry into this, in this array. At this point, you say, look, this is where we want to install our mapping. What we're going to do here is we write this physical address, which is this one. Of course, we're not going to use the lowest 12 bits because we say that we, instead of writing the address, I mean, first of all, everything is page aligned. So the lowest 12 bits are always 0. So you don't have to do anything with them. And so you say, I will mask the lowest 12 bits with the mapping mode, saying that it's, for example, read-write or read-only, and of course, a present bit as well. And then just write it here. And that's essentially how you create a mapping of this virtual address pointing to this physical address, right? That's the high-level overview of what we were supposed to do. And essentially, we do that recursively, saying that the next page, if we're mapping the entire region, like this region number 1, we say now increment everything by plus 4 kilobytes because we're going to the next page. And we do the same, but at this time, of course, this page table, this second level will be allocated, and we say we'll choose the second entry here, right? This high-level overview is familiar from last time. Everyone agrees on what's going on? Okay, cool. And then let's just essentially confirm. I mean, I gave this high-level thing, right? So the question is how to program it. Let's take a look at the source code and essentially look at this function, like kernel virtual memory alloc. And the comment tells us that we will allocate a kernel page table. Let's take a look what's going on inside. So what's going on inside is they use two functions. The first one creates this page table, and it returns us as a kernel page table directory, and it's a global variable. So I've heard some discussions about global variables just a second ago, but yes, this is a global variable. So x86 uses them, and this one will switch to into this new page table. So it will essentially take a CR3 and will assign this to a CR3 register, right? Okay, cool. So far so good. What's inside this? Setup KVM function? That's exactly what we just discussed, right? So we said, okay, we first allocate the memory for the page table directory, right? So for this first level here, because we haven't even we don't have anything. So if we want a new page table, we need to allocate memory for the new page table. Agree? Those lines do this. Agree? We're using the function of a kalloc, which gets us a page from the memory allocator. We're assigning it to the page table directory. If there is not an error, if there is an error, we return. Not sure that we check for this return value. Maybe we do, maybe we don't. But I wanted to ask you a question. And again, that's it's a little unusual, but that's the level of details which you have to have in this class. So what is the address of this page? Your reaction is probably something like this, right? That's what I see every other minute. But yes, sure. So if I ask you a question, what is the address of this variable? What is it pointing to? What is the value of this variable which we paged here? Can we figure it out? The reason I'm asking this question, imagine imagine you chose security as your profession or something, and you're trying to reason about those very corner cases where the code behaves differently, not as expected. Or maybe you want to attack the kernel, and it's critical for you to understand the value of this variable, to know where the page table directory is. Maybe you have a way of writing or reading it. Maybe you'll find a way to abuse the code. That should be after the data section. Kernel data section. Okay, let's give everyone a chance to answer. Let's try to do a poll. Meanwhile, everyone will wake up as well, which is cool. I'll give you a couple of options there, and you can choose your answer. Okay, so let's discuss for a little bit. So you say majority of people believe that this is an address of the AND symbol rounded up to the next page, right? Can someone explain the logic?
Like we're trying to use the what page for the
No, hold on, but you're making this claim, which is not like completely ungrounded, but really the page comes from the memory allocator, right? So the question is really the way to think about it is to say, okay, what will allocator return? What will it return? Do we know?
virtual address of the free.
The virtual address of a free page, but I'm asking like which concrete page? And okay, this is what the majority of people think, that they say, okay, maybe it will be the page, the first page after the and symbol, which is at this point makes sense. So this logic makes sense. You say, look, do we remember how this memory allocator was initialized? We said, okay, cool. So we remember something, that we took pages from, we took the pages right above the and symbol, and we're adding them to the allocator, right? But next level of complexity. That's a good theory. Now, can we verify that it's really the page which we're talking about? How to do that? Do we have, like, can someone confirm that this is what the allocator is doing? That it will give you this page, or how to confirm? If it's a question on the exam, I actually recommend you to quickly start x86, instrument it with a printf function and dump the address, or do the GDB and attach it and see, like, in this specific function, what is the address of the variable which is returned. But again, the goal is to learn how to reason about those things. So you had a theory as well? So if at this point we just say, okay, I have this theory, so allocator is a list. The question is like, what is at the head of this list, right? And you need to know the answer. Minus, no, like the end of the list will be, what I'm claiming is that the way we initialize the list, which we were covering last time, and I'm not saying that you'd like, the allocator returns you the head element of the list. The way we initialized the list was that we were starting from the end address, marching forward. So essentially, we started from the end and said, okay, we're gonna go to the like 4 megabyte mark, right? And essentially what was happening here, and like essentially we were using this free range function. So we were starting from the virtual start, going to the virtual end. So the virtual end page, the last page which we gave to the allocator, will be at the very top of the list. Does it make sense? And this page will be returned. Agree? Again, so why is it important? Like, again, it's a little exotic, but still in real life, if your goal is to write something into this page, into the page where the page directory, which the kernel is using, you need to know the address of this, right? And you can do different things, right? You can just dump the address and hope that it will be the same, but it's nice to understand how this address, like what semantically leads to essentially to this address, like how the linked list was allocated, what's on the top, what's the second page. Maybe you are attacking the kernel and you need to know those addresses. So that's why you kind of need to look through everything and make sure that you understand where everything is. Agree? Any questions about it? Okay, cool. So like fix your answers on the poll, because now we still have. So the correct answer will be something like the last page on the list, right? So, and it's rapidly growing right now. But not everyone is reacting. Okay, you fix, guys. I'll give you a couple of minutes just to make sure that everyone has a chance to reply. Where are we? Here. Okay, so back to the lecture. So we got the internals of the memory allocator. So we know how to what this page is about. We say, look, we got something, maybe something was using it before us. So we set this, sorry, we set everything to zeros here. In the next line, memset page to 0. And at that point, we say, look, we will implement this algorithm. We will keep track of different memory regions. We'll be walking them page by page, exactly as we described in a second. And for that, we have this helping code. We represent memory regions as a kernel map, K-map, and it's defined as an array. So essentially, and elements of this array essentially will be some data structures, which will have a virtual address, a physical address, physical start address, physical end. If we subtract, we'll have a size. And essentially, we will be using this map pages function, which will be mapping pages from each region. Just to dive down a little bit, so we will represent the address space as 4 different regions. Region number 1, this IO space used by BIOS. In your next homework, we'll be writing letters hello into this region, and they will be showing up on the screen. This is the read-only section of a kernel, so it will be mapped as read-only. Then the kernel data section plus the memory above the end symbol and sits somewhere here will be mapped as read-write. And then this additional IO space, so some devices will be using this, will be mapped as read-write. So we use this array. It's an array of data structures which have the start of the virtual address, start and end of the physical address, and the permissions. Permissions is like read only, read write, stuff like that, right? So it's, again, nothing really super extraordinary happened. We just said, okay, I want to represent memory regions. I will use this data structure, and that's how I initialize it. Question? Uh-huh. Wait, hold on. You lost me a little. Can you ask again?
Yeah.
Uh-huh. Mm-hmm. Yes, in a way, because look, in order to construct the new page table, we need these pages, like page number 1 for the page table directory, pages 2 and 3 for the leaves, right? Those pages have to come from somewhere, right? And we want to write into them. So you cannot take a page from here and write into it because it's not mapped by current page table. It's kind of a chicken and egg problem, right? So you say, look, we will only be taking pages which we're already mapping. And right now we're mapping only the pages like physical pages from 0 to 4 megabyte. And we're mapping them twice from 0 to 4 megabytes here, and from 2 gigabytes to 2 gigabytes plus 4 here, right? So the virtual addresses of those pages will show up here. And the very first page, which was returned at the poll which we had, it was this page, specifically this one, right? And so then you say, look, I will allocate those pages for the page table, and I hope I will have enough. Just enough for what? Enough to make sure that I map everything from address 0 to fizstop, like all this entire region, from 2 gigabytes to 2 gigabytes plus fizstop here. That's the goal, which we're. And you can choose different, as a designer, you can choose different regions what to map where. It makes sense because we say that the kernel and all available memory will live here for us. No, like this page table, which in the source code is called k page dir kernel page directory, will be used by the kernel for the entire lifetime of the kernel. And every time we'll be creating a new process, a process will have its own page table, because a process will have the same upper part, which maps the kernel. All processes in the system will have it. But the lower part will be different, because really like those are like different like text sections, different data sections, right? But every time we will be constructing a page table for a process, we will reuse the same plumbing. So we will reuse the same function, which initially maps the upper part, and it's not very efficient, because you can say maybe if they are identical, we can somehow share them. x86 doesn't do it. It just like creates new one every time. But it's very convenient. So this function, you will see it over and over and over. And we first will construct this upper part, and then we will be loading ELF files from disk into memory. We will construct the upper part first. We will be constructing individual lower parts for each process. So each process will have its own page table. However, there is this chicken and egg problem again. What if all processes somehow die in a system, which shouldn't happen, but maybe there is a bug, and then the kernel like is left without a single process running, so it has to run on its own page table, and it will keep using the one which we're creating right now. Makes sense? Okay, cool. Any other questions? All good? Yeah, page tables, not easy, but nevertheless, so we got this array. We said, okay, we understand. We declared like 4 regions of memory. Not surprisingly, it just says, okay, physical address 0 to physical address extended memory map at the location kern base. This kern base is defined as 2 gigabytes. So essentially, it's just a mapping of the IO space. Then the kernel link address, it's 2 gigabytes plus 1 virtual to physical conversion. So it's essentially subtracting 2 gigabytes up to the data section, because data section is writable. So this region is a text section, read-only text section of the kernel, and read-only data. And we use this linker script to make sure that the kernel is actually linked with this layout. So it doesn't happen magically. We just control the linking process. Then the data section, and from here we say from the data section to the fizstop, we're gonna map everything as writable. This is the flag, writable. And essentially this dev space, yet another constant, which is this address. And it maps to 0, but really it means that the 0 wraps around, so it will just map to the end of the address space, right? 4 regions. Fizstop is defined in a make file, and this is this constant. So it's roughly 234 megabytes. It just, the choice of those people who build x86, they said, okay, we don't want to bother figuring out how much available physical memory is in the system. We'll just take 234 megabytes and run with it, just for simplicity. And they just defined it. If you're running on a system which has less memory, x86 will crash. It will not boot. But you seem confused. So what is the confusion? Yeah. It's okay, like for educational purposes, not for like production use. And it's not very hard to figure out how much memory you have. But in real system, there will be gaps in physical address space sometimes because of the NUMA layout, stuff like that. So like all sorts of things can happen. So they don't want to handle it, just don't want to complicate. But essentially, okay, we got it. So we have the array, we walk in a for loop, 4 iterations for this array. And each time we just use this function, which is map pages. And this map pages will do exactly as we just described. We said, okay, remember, it will take a page, split it into 10, 10, and 10, and 12 bits and stuff like that. So let's go into this map pages. So here we're passing the virtual start address. We're passing the size. We're passing the physical address where this virtual start will be mapped, and we're passing permissions. So exactly as we want it, right? So map pages is the core function which actually implements the mapping. So I apologize. It makes sense to understand what's going on. But inherently, again, it's just this diagram which we had before. So the logic is very, very simple. So it says, okay, I will start with virtual address and actually page round it down because it wants to map this page to the first page. And I will start with this virtual address plus size -1 to get the last. And essentially we'll run in a loop as we were discussing. And you can say, look, sure, I will implement this loop differently, but it's okay. This implementation is fine. So, and again, so this is the example this is probably one of the first examples when it's time to start reading the source code of x86, right? And I will be asking questions like similar to what was the address of this very first page, which allocator returned. That's a simple question which you can see on the exam. So like, the idea is that you can actually read through the source code of x86 and I explain enough of it that you can reason about and answer those questions, right? And so, again, what is the outline of this loop? Remember this diagram. You say, look, we already allocated this page table directory, right? So we have it. We take the virtual address, we split it into 10, 10, and 12 bits. This 10 we use an index as into the page table directory. And if this already has a valid pointer pointing to the second level, we'll just use the second 10 bits to locate the entry in the second page table directory. And the end goal is to write the physical address, right? So the address of this, we will call it the page table entry. So really, we just want this entry in the array. And what the code will do for us here, we say, if we have this PTE here, a pointer, we'll just write the physical address with permissions and with the present bit, right? Very simple. However, we need to figure out this address. And what we use here, we use this function, which is a helping function, which walks the page table, potentially allocating additional levels of the page table, and it returns the address of the page table entry, right? So on my figure here, if I erase everything, it will be PTE will be pointing exactly here, right? And so if you do some like dereferencing this pointer, you say star, you can do PTE, P, and other flags, right? Make sense? So the walk page table directory starts with the page table and with the address, walks it and locates you this entry. Make sense? Let's take a look at how it's done. So and that's what happening. So how do we walk a page table? So the page table, again, so not super surprising. So you take a virtual address or a linear address, split it in 10 things. This point into the entry in the page table. If this is allocated, it will point to this entry, to this level. Then these 10 bits will be used as an index into this second level. And this, something what is circled with red here is your PTE entry, which you care about, right? Okay, so we start with the top 10 bits with these 10 bits of the address. How do we get this top 10 bits? What will be the code? What the code will look like? Like you have the entire thing, virtual address, which is all of it. How do you take the top 10 bits? Exactly. So you're going to right shift by 22 bits because this is 22. Okay, so x86 does exactly this. So it says, okay, you pass me a virtual address. I will have a macro, PDX, page directory index, which just extracts this top 10 bits from this virtual address. It's very easy. So you say, look, this is the macro. It takes the virtual address. It shifts it. This is actually unnecessary. You don't need to end anything. So you say like the top bits of the address should be zeros. So we only mask with the lower 10. But I think when you right shift it, it's not a circular shift. So it will be extending the address with zeros, right? Sure, makes sense. That's the source code from x86. So similarly, if you want to extract these 10 bits, the middle 10 bits, here you shift by like instead of 22, you shift by 12. Here, you really have to mask because the stop bits will still stay around. So you have to like make sure that you erase those with zeros, right? So that's what the masking is about. And that's exactly what's happening. So if you say, I started with a page directory address, I will take the virtual address, I will shift it by 22. So exactly this 10 bits will be returned as an index here. Page directory is an array. You get the entry from this array, page directory entry. You check here if this entry is present, meaning that it was already allocated, right? If it's not allocated, you go here and you say, look, someone will pass me a flag, and this flag control whether I should allocate additional levels or not. Imagine, yes, the flag is true. So you say, let's go to the next, to the memory allocator. It will give us a new page. You get this page here. You set it with zeros, and of course you want to connect them. So what you're saying is that you got this entry. It's an entry in the page table. This is a page table directory. You got this entry, which is, we call it page directory entry. You allocated a new page, which is page tab, page table, and you need to connect. So you need to write something into this entry to make sure that you correctly install a pointer here. Agree with this? And so this is exactly what we're doing here. We say, since the page tables need to have physical addresses, and this is a page tab as a virtual address, we will use a macro, virtual to physical conversion, and we'll just write it into this entry. So this is dereferencing a pointer with a page present flag, page writable, and page user accessible. A little obscure, why would that be user accessible? That's okay, we will stop it at the next level of translation, although it's just for generality of the code, so you can reuse this function for user level code as well, for mapping user level code, right? But makes sense. So essentially, the only magic, which unclear magic, is this macro. So how do you think we can convert from virtual addresses to physical addresses? Anyone?
Subtract.
Correct. You just subtract 2 GB because this is how we mapped everything with a 2 GB shift. So if you have a virtual address here, so we know that it's the same 2 GB shift. So if you take this virtual address, subtract 2 GB, you will get a physical address. And this is what this macro is doing, right? Okay, sure, works for us. So, and at this point, we say, well, it's either that we immediately had this page that we had the second level. So essentially, the goal of this function is to figure out the address of this, right? And so this is what we will be returning. Since we either allocated this page from the allocator here, page tab, or we already had it allocated. And at this point, we just say, look, we have the entry in the page directory entry. We essentially convert it to the address, convert it to a physical address, meaning that we have a pointer to this page tab here already. So if we reuse it second time, and what we're doing here, we're using the middle 10 bits of the address because this page directory index is returned by this macro. The middle 10 bits are returned by this macro page table index. It's essentially shifts by 12 and masks the lowest 10 bits. So it returns you, and you take an address of this, right? So it's essentially what you're returning here is you're returning the address of this entry. Agree with this? And okay, so that's sufficient. So we say, look, I'm explaining what I'm doing here. I'm explaining the magic between these two macros. And the deal here is that since this entry will contain some flags in the lowest 12 bits, we have to ignore those flags because we want to, like, otherwise it will lead us to a different address. So what we're doing here, we just like extend those. We take the value which is there in the page directory entry and extend it to the address, just essentially erasing the lowest 12 bits to zeros. And then we're using this macro which converts from physical, because the entry contains the physical address. We convert it from physical to virtual, and the conversion is essentially, if you take a physical plus 2 GBs, because this is how everything is mapped, you will get a virtual address. So this macro P2V just adds 2 gigabytes, right? So not super complicated. And so what we end up having is that essentially we're returning the address of the page directory entry, right? Agree? Any questions about it? Question? Yeah. So the goal, remember, the goal is to, yeah, it's kind of a little, it's easy to get lost. So the high level goal is this. You say, look, I have a function which is called map pages. Map pages works in the region of memory. It takes a region as an input. It has a start, which is a physical start. It will have a virtual start, and it will have a size, right? And map pages says, okay, I will take and map all the pages of this virtual region consecutively into the pages of this physical region, right? What does it mean to map? Map means installing correct entries into the page table, right? Because the page table converts from virtual addresses to physical, right? Correct. We're building a 4 kilobyte page, a page table which uses 4 kilobyte pages. But in general, it kind of doesn't matter in a way. So the same code, or conceptually the same code, can be used to construct any page table. It's just that it will be simpler. There will be no second level, for example, if you use 4 megabyte pages, right? The idea is to learn how to construct any page table. And at this point, we say, look, we will be constructing a page table which uses 4 kilobyte pages, right? How to construct a page table. So you say, look, I know that I need to figure out like this virtual 0, virtual 1, virtual 2, the addresses of all the pages in this region need to have mappings in the page table. They will go consecutively one by one, right? But they occasionally, of course, split, and you might have to allocate another level, right? And maybe spill into this other level, right? But for each of these entries, when you have a virtual address, you say, I will walk the page table, make sure that the second level is allocated. I will figure out, let me change the color here to blue. I will figure out the address of this entry in the page table. It's just, think of a page table as an array. So you just get you want to update the element of this array. And what you want to write there, you want to write there a physical address plus some permission bits, right? Agree? So that's the high level. In order to implement this logic, you use this helping function, walk page table directory, which takes the virtual address, takes the root of the page table, and walks it to essentially return you this element of the array, which you have to update with the physical address. That's what you're doing here, right? It's kind of conceptually very, very simple. It just, when you look at it for the first time, it like, yeah, I get it. Like there is a lot going on. But if you look at it second time, I'm pretty sure it's not hard. Almost. No, not exactly. So we're not trying to replace anything. So the way we started this function is we said, look, we want to construct a new page table. brand new. We will never use the old one. So what we're gonna do, we're gonna allocate the page table directory as the first step here. We're not gonna replace anything. We'll just first allocate it from scratch. We'll set it with zeros. It will be empty. Everything will be zeros here, right? So no mappings present, right? Then we will use 4 different regions of memory which we care to map. And for each of these regions, we will use this helping function, map pages. And map pages maps a region, starting from the virtual address and a physical address, and then mapping consecutive range of addresses of this size, right? And then internally in this map pages function, we will say, look, internally inside the map pages here, somewhere here. Everything is lost. My computer is tired. Maybe it's running out of battery. Let me just show you. We say we will running in the loop. Second. It's here, still moving like crazy. End of it. And then first go a little back. the code of the kernel, and then, you know, everything goes out because it will be hard to debug. You will not crash immediately. You will execute a bunch of weird instructions and then crash later. And so most likely it's not a fun game. And you say, look, to prevent those bugs, you say, I'm gonna map it as read-only, right? Make sense? And if you do this, it splits this one region into three, because you say, I will write this one as read-write, and I will map this one as read-write, and the middle one as read-only. And that's how we end up with 4. Does it make sense? So the high-level goal is that this region is isolated, and this region is we want to map it as read-only. Good. Okay, so we did this page directory entry. We essentially, what we're doing here, we return it from the walk page table, right? So essentially, the moment we got this element of the array, our job is very, very easy. We just write the physical address plus the permission bits, which we got from here, plus the present bit into the page table entry. And if we reach the last element of this region, we're gonna break and exit the loop. If not, we simply increment and go to the next page, right? It's a very simple code. And if we did everything correctly, by the end of this code, we exit from this function, set up kernel virtual memory. It returns us a new page table. This page table maps these 4 regions, just exactly as we described. And the very last thing which we want to do, we're going to switch to this new page table. And it's very easy as well. Remember that hardware register CR3, control register 3, contains the physical address of the page table. Since this variable holds a virtual address, we use this v2p macro, converting it back to the physical address. And this, it's a helping function which uses a bits of assembly inside. We just load this physical address of the kernel page directory into the CR3 register, right? And that's essentially what we wanted to understand today. We switched to a new page table. That previous page table, which we used before, entry page table, which mapped memory twice, is no longer in use. We're using a single page table. It uses everything, it maps everything once. And essentially, the regions which are mapped, they look like this in virtual address space. If this is a 2 GB, this one is read-only, this one is read-write, this one is read-only, and then at the very top, this is the fistop. And this is the upper BIOS region. This is the 4 GB. And this is all virtual memory. And only this is mapped. And everything is like, these guys are mapped with a 2 GB shift. And this guy is mapped 1-to-1, right? So if this is your physical memory, and this is your virtual, anything from address 0 in virtual to 2 GB is unmapped. So if you try to access it, you will get a page fault. If you try to access those regions, you will be fine. You will be accessing this memory. And if you're accessing this upper region, it goes directly to this BIOS region here. And that's the page table we will be using in x86 for the lifetime of the kernel. Make sense? Okay, cool. So then a tiny recap, what did we achieve in these last 2 lectures? So we created a tiny memory allocator, which can give us a new fresh page. And we created a new address space, a new page table for the kernel. It uses 4 KB page tables. And this is enough for us to start essentially thinking of creating the first process. So essentially, we covered these first 2 functions in the kernel. We'll talk a little bit about initialization here, but essentially at the very, very end of it, we will be running the very first process, right? So let's come back to this on Thursday. That's it. Thank you so much.